Okay, so welcome back. This is the first lesson in the Entropy pack. I know some of you have already started this, but I'm just going to go over the first bits because some of you haven't started it. So you're going to need a calculator, okay? You're going to need a pen, obviously, and you're going to need your notes. So make sure you've got all those available, and then we're going to start on page 2. So the first law of thermodynamics states that energy cannot be created or destroyed. It can be transferred from one place to another, and in that transfer you can get it to do something useful. We call that work, and that's what we studied basically in the energetics topic, which you've just finished. However, in this topic, we're interested in the second law of thermodynamics. So I don't have very many chemicals to play with, so you're going to have to bear with me here. So here I have a very simple glass of water. Now there's nothing fundamentally in the first law of thermodynamics that says that this water in here, half of it boil and half of it freeze, because I wouldn't actually be creating or destroying any energy. I would simply just be moving that energy around the place. So there's nothing fundamental in the first law that says that that couldn't happen. As long as I'm not creating any more energy or getting rid of any energy, how that energy is arranged is not covered by the first law. But how the energy is arranged is covered by what we're going to be studying in this topic, which is the second law of thermodynamics. And although it is the second law, it's arguably more important even than the first law. So we're going to have a look at that. Now, if you were in class, we'd obviously be stopping here and doing a little practical. Can't do the practical, but I am going to talk you through it. So we're going to have a look at page 2 and those practicals. Okay, so the first reaction we're going to look at on your page is HCl and magnesium ribbon. And basically what we'd ask you to do is measure the temperatures, and then you're going to draw an enthalpy level diagram for that reaction. Move that just up a bit. So an enthalpy level diagram, you're just going to draw, pen works. This would be an exothermic reaction. So you're starting with your products, your reactants here. So you're starting with magnesium and hydrochloric acid, and they would react exothermically. So the arrow's going down the page to make your products, which is magnesium chloride and hydrogen gas, and that gives off some energy. Okay, we would do the same with sodium chloride and hydrochloric acid and sodium carbonate. And again, that is an exothermic reaction. So we start with HCl and Na2CO3. And we're going to react those to form our products. I'm going to need 2 of those because we're going to get 2 NaCl and H2O and CO2. And again, arrow going down the page because this is exothermic. So basically what we're saying is that the chemicals are losing energy and the surroundings are gaining them. We've got these 2 ideas, system and surroundings. Now in thermodynamics, system basically means what's happening to the chemicals, and surroundings basically means everything that is not the chemicals. So it's a pretty big surroundings. So those are the first 2 experiments, both exothermic, both spontaneous at room temperature and pressure. Turn over to the next page. We've got 2 more to do. This one, it's a solubility. So we're basically just dissolving a salt in water. So I've got ammonium, ammonium nitrate and water, and they're dissolving, or that's dissolving to form ammonium ions and nitrate ions. So they're both aqueous now because they were solid to start with. Okay, and that's an endothermic reaction because obviously the arrow is pointing up. Moving down to the last one, you've got ethanoic acid and ammonium carbonate. Again, this is an endothermic reaction So we're going up the page. I'm not going to put all the chemicals in this time, save a bit of time. So again, it's an endothermic. The important thing there is you've got 2 exothermic and 2 endothermic reactions, both of which we say go, both of which are what we call spontaneous. Okay, so it can't be enthalpy changes alone that determine whether or not a reaction goes, whether or not it happens at room temperature and pressure. If it was only enthalpy changes which determine things, there wouldn't be any endothermic reactions which are spontaneous, because if you like, they're going up a hill. Okay, the chemicals are gaining energy to become the products. So we can understand exothermic reactions being spontaneous, but energetics doesn't explain how endothermic reactions are spontaneous. What we need to consider is the spreading out of that energy. We need to consider the second law of thermodynamics. So we're back on our page, and we're at the top of page 4 now. So we've got to understand now how a reaction can be spontaneous despite the fact that it's an endothermic reaction. And we have to introduce an idea called entropy. Now, your board allow entropy to be a measurement of disorder. Personally, I don't particularly like that idea, but it gives us a general starting point. I prefer to think of entropy as the ways that things can be arranged in my material. Now, there are a couple of really good video clips on this. There's the 60 symbols one, which is given at the top of the page. They've done several goes at doing entropy, so it might be quite useful to have a look at their different videos on entropy. And the professor there has the same problem I do with this idea of disorder as a measurement of entropy. Again, as I said, it's acceptable, but it's better to think of it as entropy as the number of ways that things can be arranged. That's both particles and energy. Okay, so there's some bits there for you to read. So what I suggest you do is pause the video and have a read through those pages and have a think about that. Okay, so at the back and at the top of page 5. So we're going to introduce something called the third law of thermodynamics, and basically that says only the entropy of a perfect crystalline substance at 0 degrees Kelvin is 0. In other words, everything has an entropy associated with it, because quite frankly we can't get a perfect crystal, and even if we could, we couldn't get it to 0 degrees Kelvin. Okay, so what we're going to deal with is the standard molar entropy, and we give it the symbol S, and it's got this little kind of underground sign here. That's telling me I'm doing it under standard conditions. In other words, for a chemist, that's 298 Kelvin, 1 atmosphere. Another way of saying that is 100 kPa, and we usually nowadays we deal with 100 kPa because kilopascals are SI units. Now, I want you to really star this bit, units. Units cause more issues in this topic than pretty much anything else. The reason for this is the units for entropy are given in joules per mole per Kelvin. Pretty much all other energetic quantities are given in kilojoules. So you've got to be very, very careful that you make sure you're converting either between kilojoules and joules or joules and to kilojoules. But you have to have things in the same units. So if one of your components is in joules, all the others do, or you need to convert that into kilojoules before you start. Okay? So, we're going to discuss in this little section the entropy of the chemical, so the entropy of the system. All right, so we're going to deal with surroundings later on. So I've got here 3 states of matter: solid, liquid, gas. So I'd like you to pause the video, have a go at doing this table. Think about which one of these 3 is going to have the highest entropy, the most disorder, the most ways of arranging those particles. How much is going to be the middle, and what's going to be the lowest. So hopefully you're back now, and I'm just going to go through that table. Okay, so gases have the highest entropy, so that's high, very high. Solids have the lowest, and liquids are kind of in the middle. And that's because of how those particles are arranged. So in a solid, their particles are fixed. They can vibrate around their points, but they can't move around too much. And they're generally speaking in a regular pattern. Liquids, they're relatively close together. And the particles are random, but there's not a lot of space between them. Oh, there's still, you've still got them packed. They still take up the shape of the container. Whereas gases are widely spaced apart. And they are random. Very random. I would put V in front of that for very random. Okay. They also, generally speaking, have higher energy. So not only the particles have more space to kind of arrange themselves and more ways that they can arrange themselves, but they've actually also got more energy, more packets of energy, we call that quanta, to arrange, because they tend to be of higher energy than their liquid or solid counterparts. So we can express this in this this chart at the bottom of the page. So why are there sudden jumps in the entropy levels at the melting and boiling points? Also, you might want to explain why there is this general increase. Okay, so again, pause the video, have a go at that question. Okay, hopefully you've paused the video and you've had a go at that question, but I'm going to go through it. So, you've got these general increases because we've got a general increase due to more kinetic energy. I.e., as the temperature increases, the kinetic energy of your particles increase, so you've got basically more quanta of energy to arrange. The more things you have to arrange, the higher the entropy is going to be. So that's the general increase. The jumps come because we're moving from a low entropy solid to a medium liquid to a high entropy gas. And just there are simply more ways of arranging the molecules in the gas phase than there are in the solid phase. Okay, so last page for today. So we can turn over. I'm going to look at the top of that page, and we're just looking there at water. So water goes from a solid to a liquid to a gas. And you should see here that the entropy increases as we do that, as we would expect, because we're going from a solid to a liquid to a gas. So the number of ways of arranging the molecules increases, i.e. there are more what we call microstates. So there are more microstates, more ways of arranging both the energy and the energy levels. So therefore the entropy is increasing. Okay. Now, last bit for today. Entropy changes during physical or chemical processes. So again, what I'd like you to do is pause the video at this point and work out whether you expect those to be a positive or a negative entropy change, and then say why. So as we pause the video, restart it, and I'll go through those 4 questions with you. Okay, so we should be back. So steam, which is a gas, condensing to water, which is a liquid. So my entropy change, my delta S, is decreasing. You're going from a high entropy to a lower entropy state. Okay, because basically you're moving from a gas to a liquid. So less microstates or less disorder. You can use disorder because your board allow it. Okay, so you're going from a gas to a liquid, so there's less disorder. Solid CO2 sublime. So in other words, solid carbon dioxide is turning into gaseous carbon dioxide. So that's delta S increasing because you're basically going from a solid to a gas. So there's, again, more microstates, more disorder. Okay. Next one. This time you've got two gases, but we're going from 1 mole of gas to 2 moles of gas. So again, here, delta S total is, or sorry, delta S of my chemicals, my system, is increasing. Why? Because I'm going from 1 mole of reactant to 2 moles of product. So my entropy is increasing. So there are several ways you can increase entropy. You can change from a solid to a liquid or a gas, but you can also change the number of molecules that you've got, the number of moles that you've got. And here I've got 1 mole, and here I've got 2 moles. And they're just simply more ways. Remember, entropy is a kind of measurement of the ways of arranging things. There are more ways I can arrange 2 things than I can arrange 1 thing. So entropy is increasing. Now this last one is quite difficult. It's difficult because we're going from a liquid and a gas to a liquid and a gas, so there aren't changes in states. We're going from 8.5 moles on this side to 9 moles on this side, but this is a slightly more complex liquid than this one, and so on. So we're not 100% sure what's going on. Our number of moles of gas is decreasing. So it's very, very difficult to actually work it out. So I'm just going to put delta S question mark because I'm not really sure what would happen. But as we're going to see in the next video, there are actually ways of calculating this. So that's what we're going to do in the next video. We're going to calculate how we can actually work out this delta S for my chemicals, my system, using my data book. Okay. Now, last but not least, we've got down the bottom of the page our summary. Okay, so our entropy, that's measurement of the disorder, or the number of microstates, or the ways of things that can be measured. Okay, so going back to my glass of water, which is what I started with. So I said at the start, there was nothing fundamentally in the first law of thermodynamics that says that this water couldn't half of it spontaneously boil and half of it spontaneously freeze. I wouldn't actually be creating or destroying any energy. But that doesn't happen. That doesn't happen not because it breaks the first law, but because it breaks the second law. And the second law, which is all about entropy, basically says that for any spontaneous reaction, there has to be an increase in entropy. And this liquid water suddenly going into the ordered state of a solid and the disordered state of a gas, rather than staying as the mixture of particles that we've got in liquid, that would disobey the second law. That would be creating order. That would be a non-spontaneous reaction, therefore. So we never see this happen. It's not because, as I said, it breaks the first law, but because it breaks the second law. And the second law, very important, and we're going to study that over the next few videos. So, cheers.